Hello, a great welcome to the series on Abaqus. Myself Jarajan P. This is tutorial number 15 and provides the design of a beam-to-beam partial depth and plate bolted shear connection. So let us first see the problem statement. So the 3D model developed in Abaqus for this tutorial is shown here. It essentially has three components. That is, one is a supporting beam, which is of size 610 by 229 by 140 UB. Then we have the supported beam that's of size 533 by 210 by 92 UB. And to have this connection, we have used an end plate of 200 by 430 by 12 mm thick, and that is shown here. And 12 numbers of MTT bolts are used to make this connection. The bolt dimensions are taken directly from the European standard. The shank diameter is 20 mm, and the length of the shank is selected based on supporting beam web thickness and the end plate, and it works out to be 25 mm. Please remember that in these connections, the end plate is normally sharp welded with the supported beam, and then the assembly is connected with the supporting beam with the bolts at the site. The properties of the structural steel and the bolts used are shown here. The Young's modulus of elasticity is 2.1 into 10⁵ MPa, and the Poisson's ratio is 0.3. We have used S275 grade steel both for the beams as well as for the end plates. Accordingly, the Fy will be 275 MPa and the ultimate tensile strength will be 430 MPa. The plastic strain at this Fu level is taken as 0.178, and the corresponding properties of the bolts, which are based on the selected class of 8.8, is given here. We have Fy of 640 MPa and the ultimate tensile strength, it is Fu, that is 800 MPa, and the plastic strain at this level is taken as 0.1. Please remember that in this case, the required shear loading is mobilized through a displacement loading U2, and the displacement loading is shown here. It is applied over a time span of 1 second, and the maximum value is 5 millimeters. Please remember that this maximum value of the displacement is pre-calculated based on the shear capacity of the supported beam at the end plate, and we calculated this shear capacity of the order of 650 kilonewton, and to mobilize this 650 kilonewton we pre-calculated the displacement requirement as of 5 mm. So let me proceed to the abacus. So referring to the model tree, you can see that yes, we have 4 parts, and each part corresponds to bolt, end plate, main beam, and the secondary beam. So let me quickly take you to these parts. So first let us start with the main beam. So please remember, this is a tutorial. I am not going to discuss in detail the development of these parts. If you are interested in how the parts are being developed, how they are being properly partitioned, please refer back to our old tutorial, that is tutorial number 12, that discusses in detail how these parts are being developed, how the proper partitioning is to be done in order to ensure a very good meshing, etc. So as you can see that this is our main beam, or what we call as a supporting beam. You can see that the supporting beam, it has 12 numbers of holes in order to accommodate the bolts, and each hole is of 22 mm diameter for MTT bolts, and you can see that these are being properly partitioned in order to ensure that the stress calculations are being done properly around the holes. Now one more thing, the total length of this supporting beam is kept equal to 1.2 meters. So that's all. You can see that yes, the partitioning is also done across the cross section. Now let me take you to the next part, that's my end plate. Yes, as you can see that the end plate is of 12 mm thick, and as similarly again the 12 numbers of holes for the bolts. And see that we have drawn an additional circuit around each of these bolt holes to ensure that the meshes are being properly streamlined. Okay, and ensure that yes, this entire rectangular plate is being properly partitioned, so that we'll be able to develop a very suitable mesh for this component. Now let me take you to the next component, that is my secondary beam. Yes, this is secondary beam, means this is our supported beam, and as you can see that it's a very simple model, and the beam length is 800 mm, and please note that there is a notch in the connect, that is a cutting the top flange as well as a certain depth of the web. Please ensure that this is done so that there will not be any clash with the main beam and the secondary beam when they're being assembled at the assembly module. Okay, and as you can see that we have partitioned this into three parts, and we expect a stress concentration near these parts so that they are being partitioned near the web portion and also at some distance from the face of this web. Okay, that is regarding the secondary beam. Now also we have got this is the model for our bolt. Okay, and ensure that here again a proper partitioning is required. As you can see that we have done a partitioning in at four locations, that is along the vertical as well as the horizontal diameter, and we also created a partition at the intersection of the shank with the head. Okay, so that's all regarding the various parts, and please remember that a detailed explanation of how these parts are being developed, this is not attempted here because that will take away a lot of our time during the presentation. Now similar to this, I want to show you the material properties also, because this also don't require much of explanation. Remember, we have two properties, one for the structural steel, that is basically for the beams as well as for the end plate. And as you can see that yes, we have a Young's modulus of 2.1 e raised to 5 as a 10 raised to 5 Newton per mm square, and a Poisson ratio of 0.3. And as you can see that in the plastic we have defined a yield stress of 275 and an ultimate stress of 0.430 MPa with an associated plastic strain of 0.178. That is all regarding the property definition of the structural steel. And coming to the bolt, as you can see that yes, we have the same set of elastic constants. Only difference is that in the plastic property we have as yield stress of 640 and an ultimate stress of 800 Newton per mm square, and with an associated plastic strain of 0.1. And we have already created a section and assigned these sections to these components. As you can see that the color of all these components are turned green because all these properties are already assigned. Now let me take you to the next module, that is the assembly module. Obviously we know that assembly is the module where the different components or the different parts are to be assembled. So let us start creating the various instances. So we'll start with the main beam. Okay, fine. So as far as the main beam is concerned, we need not have to do any modification. So let us first now next create the instance for the end plate. Okay, so end plate, so that's okay. So as you can see that first of all the end plate need to be rotated. Okay, so let us rotate the end plate first. Fine. Okay, fine. So you can see that yes, it is properly rotated by 90 degrees around the y-axis. Now let us shift this end plate using the coaxial requirement that the holes in the web and the holes in the end plate need to be coaxial. So let us do that using this constraint, coaxial constraint option. So please ensure that yes, we have selected here the first hole. So obviously we need to select the first hole in the beam web portion also. Okay, fine. So let us see whether the normals are pointing in the same direction. That's okay for us. Okay. So you can see that. So the end plate is now shifted so that all the holes are coaxial. Now let us adjust the position of the end plate. So that should be done using the face-to-face constraint. And that the normals are in the same direction, there is no issue. And this distance should be the 12 mm. Okay. So as you can see that yes, we have a properly positioned the end plate. Okay, and you can see that both the holes are coaxial. So having done that, let us proceed for creating the instance of the bolt. Okay, so as you can see that yes, the bolt is to be rotated first by 90 degrees. And remember that this rotation has to be done about the y-axis. Okay, fine. So the bolt is rotated. Now we need to translate this bolt so that it is a coaxial. Is a shank is coaxial with other halts. So let us again, as usual, go for the coaxial constraint. So as you can see that yes, the normals are not pointing in the same direction. So let us do a flipping. Okay, fine. So as you can see that yes, let us see where is the position of this bolt, whether it is a coaxial or not. Okay, fine. This is the position of the bolt. The only thing is that we need to adjust the position of this bolt, okay, along the x-axis. So let us go for the face-to-face constraint for the same purpose. So face-to-face constraint. So this is a mobile instance, and this is a fixed instance. And let us see that the normals are in the same direction. Yes, they are in the same direction. So this distance will be obviously 13 mm. That is nothing but the head thickness. So let us see that whether it is now correctly positioned or not. Yes, as you can see that the first bolt is correctly now positioned. Now let us proceed for creating an array, a linear array of this bolt. So we'll go for the linear array. So we need to create the done. So now we find that there is some problem with this distance. So it is not getting properly translated in this direction. It means that we have to select the direction properly. So this is the direction which I want. Okay. So let us say we know that this distance should be 140. Okay. And we require 6 numbers, right? We require 6 numbers at 70. Okay, 70. Yes, you can see that is properly. That's okay for us. Yes. So we find that. So let us look into the visor plane. So we can see that yes, the bolts are also properly aligned, properly positioned. So let us also see the other side of the web, because this is required to ensure that yes, as you can see that yes, the bolts are being correctly positioned. There is no issue as such. So accordingly, let us create the instance of the final component, that is our secondary beam. That is auto offset. Okay. So as you can see that yes, this instance need to be first of all rotated. So as usual, let us go for rotating instance. So we shall proceed for rotating about the y-axis. So let me provide a rotation of minus 90 degrees. That must be okay for me. Good. So let me say that this is okay. So now what we need to do is that we need to shift this secondary beam to the other side of the main beam. So this can be easily done using the translate option. Translate. So select the entities. So we need to translate the entire one. This is okay. So now let us start selecting the start point. Okay, this is the start point. Okay, now let us go for the end point. So let us create, so let us select the endpoint. This endpoint must be this one. Okay, fine. So this is okay. So now let us see the entire assembly. Okay, so you can see that yes, it is being properly aligned. So let us see the view from the various angles. So zoom here. So as you can see that yes, the top of the web is aligned exactly with the top of this end plate, and you can see that the top of these two flanges are in the same position. And please also look onto this cut that we made onto the beam web. As you can see that it clears the flange of the main beam. Okay, and therefore we can see that the assembly is properly generated. The assembly of the entire model consisting of all the four components is generated. So now coming to the step module, you can see that we have already created a step known as the step displacement, and the procedure that we have used for this tutorial is the static general. So if you want to see the details of this step, you can just edit it, and here you can see that the time period is set as 1, and the nonlinear geometry option is kept as on, and we have set the automatic stabilization for the convergence to solve the convergence issue as the specified energy fraction option here. You can also set some other options as per your requirement. And coming to the incrementation, you can see that we have fixed the maximum number of increments as around 10,000, and the initial increment size is 0.01, and the maximum is 0.015, and the minimum is 1e minus 15. So, and as this involves the friction, we have set the equation solver there's a matrix storage as unsymmetric. So that's all regarding the steps module. Now you can also go for defining the so-called field output variables. So for example, if you let us just see whether any variables are being defined. Yes, so you can just edit it, and so obviously we may have to go for the stresses, that's the von Mises stresses, then the passive strains, the displacements, forces, and the contact everything. Okay, so the proper field output variables are to be mobilized in this module, and please ensure that only those field output variables are selected so that that will not impact the execution time in Abaqus. Okay, so now we are ready to proceed to the interaction module. And before going to the interaction module, I want to tell something about the reference points. So if you see this diagram, we have already generated 3 reference points. For example, if you go to the assembly module, see right now I am not generating anything because that will eat away majority of our time. So if you see this, we have created 3 reference points. RP1, this is my reference point RP1, and RP2 is the reference point at the other end. And remember that RP1 and RP2 are generated. First apply the boundary conditions later in the loads and boundary condition module. And these reference points RP1 and RP2 are tied to the entire cross section through the coupling constraint. Okay, so if you want to see the constraint, you can go over here and can say that yes, here is a constraint RP1, and which is generated through this command. And remember that if you want to see the kind of the constraint, let me just edit it. You will find that yes, it's a coupling constraint. Okay, and similarly we have also created a coupling constraint at RP2, and at RP3 we have generated another uh, constraint. Remember that RP3 is the point generated for the application of the displacement in the coming loads and boundary condition module. And as you can see that RP3 is again tied to the entire cross section through the coupling constraint. So this is all regarding the definition of the reference points through this label, and also the definition of the proper coupling constraints through this label. Okay, fine. So now let us proceed for the definition of the interaction property. Here again I have defined it actually for the convenience. So if I edit it as normal, you can see that yes, the tangential we have applied a penalty function, and let me keep it as instead of 0.05, 0.3, 0.3, and then the normal we have kept it as the hard contact, so that is okay for us. So yes, save it. So we have defined the interaction property. Now we are going to, as you can see that here many surfaces are in contact. So selecting the various contact pairs by hand is a time-consuming task. So you can quickly make use of the facility already available in Abaqus interaction module, that is finding automatically the contact pairs. So just press this. So let us keep the separation distance of 1 mm because we know that the holes are a little bit larger, and let us ask Abaqus to automatically detect those contact pairs. So we'll just press the find contact pairs. So you can see that it is a yes. So you can see that yes, it has already spotted 50 contact pairs. And here I want to highlight a little bit of an important thing. For example, if you want to see each and every contact pair, what you need to do is that you have to just select it. For example, if I select this, so you can say that yes, it is, for example, yes. So you can just zoom it what it is, what this contact pair is about. Yes, you can see that it is the contact between the head of the bolt and the end plate. Okay. Now similarly, if you go down, you'll find that there is a contact that is highlighted by uh, okay. So that is connecting the end plate and the secondary beam. So let me just spot that. That is a secondary beam. So maybe that it is somewhere here. It's an end plate, and yes, it is here itself. I think yes. Okay. So look here. This is basically Abaqus spotted it as a contact pair. Yes, it is in contact, but this is not actually this particular web. It is a tied. It is not actually a contact pair, interacting pair. Basically, what we want is that we know that this web of the secondary beam that will be welded, okay, to the end plate. So what we can do is that we can just delete this. We can delete this interaction because this interaction we are not interested in, that is between the secondary beam and the end plate. So what you can do is that you can just select this one, and then you can go for deleting it. Okay, so you can, if you want to see the edit, suppose that you want to see uh, the property of this contact pair, you can just edit it. Okay, and suppose you want to delete it, you can just delete this contact pair, just delete it. Okay, so this means that we have got altogether only 49 new contact pairs. Okay, and this is acceptable to us. And here I want to add one more thing. For example, here the adjustment. In some cases, what happens is that due to the pre-overclosure problem, we need to ask Abaqus to do the automatic adjustment. So what I will do is that I will just select this adjust one, and then what I will do is that I will go for the edit cells here, and here we can see that earlier by default Abaqus has set it as no adjustment. I want to keep it as adjusted only to remove the overclosures, because in some cases, for example, whenever we play with this similar kind of problems where we have got the many contacting pairs, there seems to be an overclosure error sometimes. So let Abaqus adjust if there are any overclosure errors, as errors if at all. So okay, so you can see that adjust the column. So that's all regarding the contact pairs. Okay, so we can say that this is okay for us. So we can say that yes, we have got altogether a 49 contacting surfaces, and all the properties have been set over here. Now regarding this uh, secondary beam web with the end plate, we need to tie these two components, that's the web of this secondary beam and the end plate, through another constraint which is already being created over here. So you can see that I have already created a constraint. There's a tie constraint. Okay, so if you edit it, you can see that yes. So this particular, if I just zoom it, you can see that this is a tie constraint that is created between the web. Okay, here we are not going to model any weld connection between the web of the secondary beam and the end plate. Instead, we are going to just do it. There is a connection between these two components through a tie constraint, and as you can see that the tie constraint is done with the web which is highlighted here in magenta and with the end plate face. So this is a very important thing. So don't miss this important constraint, that is the connection between the web and the end plate, which is done through the tie constraint command. So that's all regarding the interaction module. Now we are ready to proceed to the load module. Defining the boundary conditions. So first let us define the boundary conditions at the two ends of this main beams. So it's done by, so we will create it. So we'll call it as a BC, for example, RP1, okay, and it is defined in the initial step. Okay, we will have the displacement and the rotations as obstruction continue. So now we shall go for defining the selecting the regions. So this is my RP1, so that is done. Okay, and I will restrain in the U1, U2 and U3 directions. So it's okay, fine. Now similarly let us create one more for the RP2. We see RP2. Okay, so the displacement and the rotation is okay for us. So continue. Now let us just select the regions. So that is nothing but my RP2. That's okay, done. And let us again restrain it in the U1, U2 and U3 directions. Okay. Now we need to define a boundary condition at RP3. Please remember that this particular phase is considered to be an axisymmetrical phase. So it does mean that at RP3 we need to impose a axisymmetry boundary condition. So let us create it. So BC RP3, okay. So and this is the initial. So we have to select the symmetry and asymmetry option. Continue. And that is at the RP3, and so that done. So this is basically the x-axis symmetry, so select this one. So that's okay, fine. So we have defined all the boundary conditions. Now we need to define a displacement loading at this point RP3. So let us create one more thing, that is BC, create BC. This is corresponding to the displacement, and obviously this has to be creating the corresponding associated step displacement. And we will select displacement rotation options, continue, and select this RP3 point where we need to impose the prescribed displacement, done. And as you know that we won't apply to the y direction, so that is my U2. So this is my -5 downward direction 5 mm, and here I have defined the linearly amplitude function as amplitude triangle. Okay, that's okay for me. Okay, fine. So you can see that yes, we have applied all the prescribed boundary conditions as well as the displacement loading at the points in this module. Now we are ready to proceed to the next module, that is basically the mesh module. So to save the time, in fact the meshing is done in advance. So let me just show you the meshing of the various components. So for example, for the bolt, you can see that yes, it is very nicely meshed. There is no issue at all because we did the partitioning in the right way. And now coming to the end plate, so you can see that yes, so you can see that yes, the arrangement of the meshing is very optimal. You can see that there is a very right aspect ratio for all elements, and the change in the element shape is very gradual. There is no issue at all. And here one more thing, remember that for the halls, in order to ensure a good aspect ratio, you have to divide the thickness into two parts as shown here. And this is always a good practice because normally we always arrive at aspect ratio issues very near to the openings and all. So this is one way to solve such issues. Now in a similar way, if you go to the, for example, the main beam, look here, this is my main beam. So if I have the visor plane, okay, fine. So here you will find that in and around the halls we have used a little bit denser mesh, and for the other areas we have kept the meshes as normal. Okay, and here again, if you see, we have divided the thickness into two. So near the halls, here it is divided into two, so that the aspect ratio will be maintained very healthy for us. So that is regarding the main beam. And finally, looking at the second beam, we have got a very simple shape over here, but considering that we expect some kind of a stress concentration very near to this position where it is directly connected to the end plate, and also near to this point we expect some kind of a stress concentration, so we kept a little bit denser mesh here. If you want, you can also keep some kind of a denser mesh in and around this area. Otherwise, we have kept the spacing as normal. Okay, so this is all about the meshing. And here I want to tell one very important thing regarding the element type. For all the four component parts that we have discussed, element type is the same. That is C3D8. For example, if you want to see the element that is chosen for this web, it is very simple. You go over here, just select it. Okay, you can see that it is a simple C3D8 element, and I have unchecked the reduced integration for all the elements so that we'll get a precise results. Okay, so that is acceptable to us. So this means that we have completed all modules and we are ready to submit the job. Okay, so we can go directly over here. Okay, you can just create a new job, for example. So we'll just delete it. I'll delete this job. Yes, I will create a new job. For example, let me say that it is a new job, new. Okay, and then continue. So this is okay, and then you can just submit it. Okay, you can see that yes, the submission is in progress. It is submitted, and now and it is started running. Okay, fine. Okay, fine. So let us start reviewing the results. So as you can see that this is the how the U displacement varies across the model, and as expected, we have imposed a displacement of 5 mm, and that is at the midspan of this secondary beam. Now let us see the variation of the one-axis stresses. So we shall go for yes, one-axis stresses. Let us just to go on selecting the various components. That will be better for the evaluation. So let us first proceed for selecting the end plate. So we shall go for the end plate. So we'll remove other components from this display viewport. So end plate, remove. Okay, fine. So now as you can see that yes, the end plate is available to us for the review. So look here. So this is how the stresses are developed in the end plate. And as you can see that the one-axis stresses have reached a value of 281 Newton per meter square. That is very near to the yield stress of the material. Okay, still we have got some capacity in the reserve. So if we want to see how the stress has propagated all throughout our analysis step, you can see that yes, the stress around the openings are like going on increasing progressively, because those are the critical parts indicated by the red color, and that is a 280.9 Newton per meter square. That is a procedure for inspecting the stresses in the main beam. So we shall delete all the components. We shall just remove from the viewport all the components. Expect I think the main beam. We'll inspect the main beam first. Okay, so this also will remove. Okay, fine. Okay, so you can see that yes. So this is how the stress contribution in the main beam. And here again we find that the stresses are around say 280 Newton per meter square, very near to the yield stress of the material. So because we have applied a stress or applied a shear load that is almost equal to the beam capacity, that is going to be very critical. So we can see that the design conduction is very much perfect to mobilize at least 80% of the shear capacity of the beam. So you can see that how the stresses have propagated all throughout the result. As you can see that yes, the stresses around the opening, you can see that it goes on increasing, and it has reached a maximum value of 280 Newton per meter square. Now let us quickly go for the secondary beam. So let us just remove all components other than the secondary beam from this. So remove. So we find that yes. So regarding the secondary beam, we find that yes, as expected, we have got a stress concentration in and around where it is connected to the end plate, that is this saw, and also near this cut portion, we have got the stress concentration. And here again, we find that the web portion is the stresses are exceedingly high because it is around 318. It has exceeded the yield stress 318 Newton per meter square. So we can see that we don't have any problem in the flange portion. So now if you are interested in finding out the stresses in the bolts, it's the same story. What we need to do is you can select it. For example, suppose you want to select any one bolt. Okay, let us select one bolt. So you can select as a group of bolt also, no problem. So 2 I want to select. So I'll remove this, and all other components also I'll remove. Okay, fine. So you find that this is the bolt that we have in hand, and you will find that the stresses have gone up to a level of 509 newton per meter square. Now if you are interested in finding out what will be the shear forces, and please remember that if you do the calculation by hand, you won't be having any kind of a tensile forces, but obviously there are out of plane displacements, and this kind of connections will obviously put the bolts in tension as well, which is normally considered not considered in the hand calculations. So if you want to have this, so you can say that yes. So we will see that whether this is the maximum. Yes. So we find that the shear, for example, in this selected bolt is of the order of. Let me just move this section a little bit up or down. Yes. So we find that yes, the stress it is of the order of yes, it's of the order of say 40 kilonewton. So we find that for M20 we have got a shear capacity of the order of say 90-95 kilonewton. So we don't have any problem as such in the shear capacity demands for the bolts. Now the last one we want to investigate is that what exactly was the shear force that is mobilized. Okay, because we have applied a displacement of a 5 mm. So in order to have that, what you need to do is that we just go to the expert data, get the ODB field output, continue this, and we can go for the variables and select the node labels. So I will select this. I know that is it's RP1, comma RP2, okay, RP2, and we can just have it, just plot it. So we find that yes, as far as the main beam is concerned or the supporting beam is concerned, we have got a supporting maximum shear force of 0.3 into 10 raised to 6. That is of the order of say 325 kilonewton. That means adding both supports, we have got 325 into 2, that's 650 kilonewton. So means that the connection design is capable of taking approximately 650 kilonewton, though we find that with the stresses in some components like the supporting beam and the end plates have slightly exceeded the yield stress, but this connection is good enough for a total shear capacity of 600 kilonewton. So that's all regarding this tutorial. We'll come up with interesting tutorials in the coming weeks.